So we're looking at graphing quadratics in vertex form. A quadratic is an equation with a degree of 2, meaning that its highest exponent is 2. The parent graph is y equals x squared, and the graph is called a parabola. So it looks like this. Have an axis, and a parabola is that U-shaped graph. And this graph is symmetric, which means it has an axis that axis of symmetry passes through the vertex, which is h comma k, and it's a vertical line, and the graph is symmetric around that. Like, you could fold it on that vertical line and you would have the same points on the other side. So this is our axis of symmetry. And okay, so here's our first example. Y equals -3 times the quantity of x plus 1 squared. We're going to use some of our knowledge from the first unit where we learned about the vertex, knowing that this equation, based on our transformations and what we just did in the last homework, is to the left 1, but it has no vertical translation up or down. So the vertex, just like the absolute value graphs, a absolute value of x minus h plus k, our parabolas are a parentheses x minus h squared plus k. The vertex, for both cases and for all functions that we're going to do that have a vertex, is going to be h comma k. So this vertex is -1 comma 0, because this is the plus 0 out here. And remember, it's always the opposite, because this is a horizontal translation to the left one, and left one is -1. So we start with our vertex, and then we're going to make a table. Okay, so 1, identify my vertex. 2, make a table. And we know that the graph of the parabola is symmetric, so -1, 0. So I'm going to choose 2 points on either side of the graph. And because it's symmetric, our axis of symmetry is right through the vertex, the vertical line through the vertex. That's the equation x equals -1. So it has an equation. And we used a dashed line because it's not actually part of the graph. It's like an imaginary part of the graph that it's symmetrical around. And so we're going to pick points on either side of the axis of symmetry, and we're going to use reflection to put them on both sides. So I like 0 and 1. Okay, so we have 0 and 1, or we could do -2 and -3. You could pick either set of points, but we're going to plug in 2 points. So we're going to plug in 2 points on either the right or left of the vertex. So here's our table. We know if I plug in -1, I get 0. When I plug in 0, I get -3, 0 plus 1 squared plus 0. I don't need to write that. Now, it's really important here that you use the order of operations. And this is -3 times 1 squared, which is -3 times 1, -3. So 0, -3 is my next point. And then, I had a blue before. So that's my first point, and then we'll plug in 1. -3 times 1 plus 1 squared. -3 times 2 squared, which is -3 times 4, which is -12. So it's really important that you do that exponent before you multiply, and that's where a lot of people make mistakes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so this point is all the way down here. So that's the first half of my parabola. And then I can reflect this point. This point here, it's 1 away from the vertex. So at -2, it's going to be 1 away from the axis of symmetry. So that reflected point is here. Okay, so we make a table, we plug it in, and then we reflect the points along the axis. This point here is 2 away, and so we're going to go 2 this way. -3, -12, and then we can draw our parabola. I'm going to do it in black so we can see it really well. And this one should be narrower because, as we know from our transformations, this is a vertical stretch factor of 3, and it's a reflection, so that's why it's upside down. So our next example is f of x equals 2 times x minus 2 squared plus 5. So again, the first thing I'm going to do is identify my vertex. And that is going to be +2, because it's the opposite sign. This is a translation to the right 2 and up 5, so the vertex will be at 2, 5. And then it's going to be steeper because it's a vertical stretch factor of 2. That's the 2 in front. But we're not going to use that to graph it. We're going to use a table. So 2 is table. So when I draw my axis here, I'm actually going to put a good graph in here. Always looks better. My vertex is at 2, 5, so we're going to put that on the graph. And then we're going to draw our axis of symmetry because that kind of helps us visualize what x values we're going to choose. And so our vertex is at 2, our axis of symmetry is x equals 2. That's the equation of the axis of symmetry. And now I can choose to plug in either 3 and 4 or 1 and 0. 1 and 0. Okay, it doesn't matter which 2 we choose to plug in. So we're going to make our table. We know the vertex is 2, 5. So I'm going to plug in 1 and 0. Actually, let me plug in 3 and 4, just so you see plugging in different numbers this time, even though they're also on the right side. What I like about points on the right side of the axis of symmetry is they usually give me a positive inside the parentheses, and that's one less error I can make with negative signs. So I'm going to plug in 3, 2 times 3 minus 2 squared plus 5. That's 2 times 1 squared plus 5. Doing the parentheses first, then my exponent. 1 squared is 1, so 2 times 1 plus 5, that's 2 plus 5, 7. And then plug in 4. 4 minus 2 squared plus 5 is 2 times 2 squared plus 5, and 2 squared is 4, so 2 times 4 plus 5, which is 8 plus 5, which is 13. So this is going to go off my graph. I'm going to need to extend this. 10, 11, 12, and 13. So I have the points 3, 7, and 4, 13. And then we're going to use that to reflect. So that is 1 away, so I can put a point right here, 1 away. I'll put those in red. This is our reflected point. And then this point up here is 2 away from the vertex. And so we're going to go 2 away, so that'll be on the axis. And if we actually plugged in 0 and 1, we would get 13 and 7. And you can check that as well. And then we'll connect it to make our parabola. While we're here, let's talk a little bit about domain and range. The domain of all functions that are quadratics is all real numbers. I can plug in anything I want. It keeps going both ways on the x-axis. It's maybe very steep, but it keeps going. But my range is determined by whether it opens up or down, and my vertex. So my range starts at 5 and goes up. So that is a range of y such that y is greater than or equal to 5. So that k factor, that k part of the vertex, is part of our range, and it's either greater than if it opens up or less than if it opens down. Now our next example is f of x equals 3x squared plus 4. So again, we're going to find the vertex. And in this case, this is just a vertical translation up 4. So that vertex is at 0, 4. There is no number inside the parentheses, so you could actually see it as x minus 0 plus 4. Oh. And we're going to put that on our graph. 0, positive 4. And in our table, another way to look at the table is to put 0 in the middle. And 0 is our vertex, so 0, 4. And then I'm going to pick two numbers smaller, -1, -2. Those would be here on the graph. Or two numbers bigger, 1 and 2. Those would be these on the graph. And that axis of symmetry, in this case, is our y-axis, which is the equation x equals 0. So we're going to plug it in. Let's plug in the negatives just for fun, which is what I normally do not do. 3 times -1 squared plus 4. The reason that I don't like to do that is because a lot of times we forget that a negative squared is positive and that we're doing that square first. So it's 3 times 1 plus 4 equals 7. And 3 times 2 squared plus 4 is 3 times 4 plus 4, which is 12 plus 4, 16. So again, it's going to go off my graph. And 11, 12, 13, 14, 15, 16, way up here. So we have the point -1, -1, 7, and -2, 16. And then we can reflect, right? This one reflects over to here, and this one's going to reflect 2 away, 2 away. And that point's going to go here. So we reflected this one, and we reflect this one. And we should see that in the table we could also fill in these numbers, 1, 7, and -2, 16. Now this is true when the values here are equally spaced from the vertex. If our vertex is at a fraction, then like 1/4 or something, we have to look at it a little bit differently. And now let's connect this. And there's our parabola. Our domain is all real numbers. And our range is y such that y is greater than 4. Greater than or equal to 4. It's always equal to because that vertex is part of the graph. Okay, example 4. G of x equals -x plus 4 squared minus 1. So my vertex is -7, opposite from what's inside, -1. And then we're going to bring a graph in. So my vertex is at -7, -1. Oops. My axis of symmetry is at x equals -7. And I'm going to plug in 2 points greater than and 2 points less than into my table. So -7's in the middle. And I'm not actually going to plug in all 4 points. I'm just going to use symmetry to find the other ones. So -6, -5, and -8, -9. So when I plug it in, -6 plus 7 squared minus 1. That negative in front has to be dealt with after. So it's -6 plus 7 is 1. So it's -1 squared minus 1. And then 1 squared is +1. So -1 minus 1 is -2. So my point is -6, -2. And then when I plug in -5, we get Negative 5 plus 7 squared minus 1. That negative happens after we do the 2 squared. So negative 4 minus 1 is negative 5. And so they reflect negative 2 and negative 5. So negative 5, negative 5. And then the points reflect on the other side of the axis of symmetry. And then your domain is x is contained in the set of all real numbers. And my range is y, such that y is less than or equal to, because it's below the vertex, negative 1. Okay, and our last example, y equals 1/2 times x minus 3 squared plus 2. So we have a vertex at 3, 2, because remember that translation is right 3 and up 2. And then our a is 1/2, but we're just going to use that as we fill out the table. So we're at 3. And my axis of symmetry is x equals 3, because this point's at 3, 2. And then we're going to make our table. Now, we want to, sometimes when we are working with a fractional coefficient here, a fractional a, we want to make a better choice in our numbers. So we're at 3, 2. If I plug in 2, I'm probably going to have to deal with fractions. So let's instead choose 1 and negative 1, or 5 and 7. We're going to count by 2 away from the vertex and 4 away from the vertex. That's going to help keep my numbers whole instead of being fractions. So we can put in 1 and negative 1, or we can put in 5 and 6. I'm sorry, 5 and 7. So let's do 5 and 7. 1/2 times 5 minus 3 squared plus 2 is 1/2 times 2 squared, which is 1/2 times 4 plus 2. 1/2 of 4 is 2, and 2 plus 2 is 4. So the point is 5, 4. And then 1/2 of 7 minus 3 squared plus 2. 1/2 of 4 squared plus 2. 4 squared is 16. We have to square first, which is 8 plus 2, and that's 10. And so the negative 1 is also going to have a y of 4, and the positive 1 is going to have a y of 4, and the negative 1 is going to have a y of 10. And so let's put that on there. So negative 1, 10, 7, 10. And those are both the same distance from the axis of symmetry. And then at 1, 4, and 5, 4. And there's our parabola. Our domain, again, is all real numbers. All the x squareds are all real numbers. And the range is y is greater than or equal to 2.